Hello, I'm Seema and this is part 17 of the chapter States of Matter. We were solving some numerical problems based on ideal gas equation from the NCERT textbook exercises. Moving on with that, I would now like to solve question 5.9 of your NCERT text exercise, which is based on ideal gas equation. The question is that the density of a gas is found to be 5.46 gram per decimeter cube at 27 degrees Celsius at 2 bar pressure. What will be its density at STP? We are looking for initial density and final density. D1 is 5.46 grams per decimeter cube, right? At T1, temperature is 27 degrees Celsius. For the use of temperature in gas laws, we always need the temperature to be in Kelvin. So add 273 to it and you will get 300 Kelvin, right? And the pressure given as P1 is 2 bar. Now we are supposed to find out the density at standard temperature pressure. So what is standard temperature? We are looking for D2. Let us say density at standard temperature pressure is D2. Then what would standard temperature be? We know standard temperature is 273 Kelvin. And what is standard pressure? Let us call it P2. Standard pressure is 1 bar. So let us now apply the ideal gas equation to both the situations and then we will try to find out D2 from these two relationships. If you apply ideal gas equation to the first situation, we know the ideal gas equation is PV is equal to nRT. But we are not concerned with N, we want the term in density. So we know what is number of moles? PV is equal to small m over capital M, where small m is the mass of the gas and capital M is the molar mass of the gas, RT. I'm just doing the derivation here so that you know how we moved from the ideal gas to that version of it which includes the density. So we know what is density. Density is mass per unit volume. So P would be equal to mass upon volume, Rg upon M. Okay? Now, mass per unit volume is density. So P would be equal to density dRt upon M. Or we can say what is density from this? Density would be equal to P. Now we're keeping density here and moving everything else on the other side. So P remains where it is, M goes up and RT comes down. So this is the relationship for density that we get from the ideal gas equation. And we have been given one density and we are expected to find out the density under a different situation. So let us now use this formula and apply these. Now D1, what would D1 be? D1 would be P1, the molar mass 1, molar mass would be the same in the case, so I'll keep it as molar mass 1, upon R, or rather I should not put M1. Why? Because the molar mass of the substance of the gas remains the same whether it is under these conditions or under the standard temperature pressure conditions. So the molar mass is constant, so I keep it as constant. R is R, which is the gas constant, and T is T1. Do you see here? So that's D1. So let us put the values of this. P1 is 2 bar. Molar mass, we're keeping it as M upon R, and T1 is 300 Kelvin, right? And what would D2 be now? D2 would be P2M upon RT2. Just as we had D1, similarly we have D2. Let us put the values here now. P2 is 1 bar. M remains M, R remains R, and the temperature now is 273 Kelvin, right? Now, in order to get a relationship between these two, we already know what D1 is. What was D1? D1 was 5.46. So let us find the ratio between these two. D1, what would D1 upon D2 be? If we find a ratio, it would be easy for us to, since we are looking for D2, it would be easier for me. I would like to keep D2 in the numerator. So D2 over D1, let us find that out and put these values. What is D2? D2 is equal to 1 bar into M upon R into 273 Kelvin, right? And we have to divide it by D1. If you have to divide anything by D1 and it is present in this form, what do? We multiply it with by reversing making the numerator the denominator and the denominator the numerator. So when you divide it by D1, how would you write D1? D1 would be, right, the denominator on top, it would be R into 300 Kelvin divided by 2 bar into M. Now see, what all units would you be able to cancel and what values would you be able to cancel out now? M and M go, right? Kelvin and Kelvin are gone. R and R are gone. Bar and bar is gone, right? Also, we know the value of D1. What is the value of D1 here? It is 5.46 gram per decimeter cube. But what is our question? We are expected to find out D2. So keeping D2 here, so D2 would be equal to, now what are we left with? 1 upon 273 into 300 upon 2 into, we are now bringing D1 up here. And what is D1? What is the value of D1? It is 5.46 gram decimeter cube. Grams per decimeter cube, right? Now do you notice that all other units have cancelled out, and since we are looking for density, our density should be in the units of density, which is grams per decimeter cube. So when you solve this, you will get D2. And what would the value of D2 be? It would be 3 grams. When you solve this, it would be equal to 3 grams per decimeter cube. And this is your answer. Now this is the last question of this video and for this topic that I will be doing. It's a simple question. The question is, calculate the temperature of 4 moles of a gas occupying 5 decimeter cube at 3.32 bar. And the value of R is given to you. What all have we been given? The number of moles, N, is 4.0 mole. It occupies a volume of 5 decimeter cube, so V is 5 decimeter cube, and P, pressure, is 3.32 bar, and R is already given to us, right? We know, what are we supposed to calculate? We are supposed to calculate T, capital T. Now we know that PV is equal to nRT, and we've been given these 4, we are required to find out T. So what would T be equal to? T would be equal to, keep PV on this side and take NR down here. So NR, come down here. So what is T? Let us substitute the values. What is pressure? Pressure is 3.32 bar. What is the volume? Volume is 5 decimeter cube divided by number of moles is 4 moles into R. The value of R is 0.083 bar decimeter cube per Kelvin per mole, right? Now let us cancel out the units. So now since we are looking for temperature, the answer we get should be in Kelvin. Bar and bar are cancelled, okay? Mole and mole inverse are cancelled. Then decimeter cube and decimeter cube are cancelled. So you get Kelvin inverse in the denominator. So which means it is Kelvin in the numerator. And that's what we want. When you solve this, what is the answer you will arrive at? The answer would be 50 K. So temperature is equal to 50 K. So these were some numerical problems based on ideal gas equation. If you found the video helpful, please give it a thumbs up. I would appreciate that. Subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.